Okay, we are all here. Welcome back for another day of fun. Next time I'll see you after today will be for lab on Tuesday. So make sure that you remember to do the pre-lab quiz for lab on Tuesday since it'll be the first time around. We don't want Max to forget. Max, bye. Okay, today we're going to talk about electric fields. Now I got, I think, 2 or 3 slides before we get to electric fields, but not much. So first, a problem for me to work out, I suppose. A particle with positive charge of plus q is the distance r from a particle with a negative charge of minus 2q. The Coulomb force that, I can read this way. The Coulomb force that the positive charge exerts on the negative charge is plus F, where F is the magnitude and the plus sign indicates the direction of the force. What's the magnitude and direction of the Coulomb force that the negative charge exerts on the positive charge? So I know a lot of you could probably just answer this without doing anything except for, one thing. But I want to be clear. So I'm going to first, what do you suppose I should do first for solving the problem? Go ahead, Diane. Make a diagram. So I have a positive charge plus Q. It took like 3 times for it to write in the first class. But when it finally did, all of the thing I had drawn popped up at the same time. See, here we go. So here we have plus Q with a negative charge minus 2Q. So I'll put my negative charge. I'll make my negative charge a different color. Although logically we would have. So there's my 2 charges. The Coulomb force between them. Oh, and there's the separation of distance r. The Coulomb force between them is plus F, where F is the magnitude and plus sign indicates the direction of this force. What direction will the force be on the positive charge? Will it be to the left or to the right? Okay, to the right is Mr. Chapman's answer. Is that correct? Anyone else? Yes, no. Are you with David or against him?
Well, they're opposites, so they attract.
They're opposites, so they attract, which means David was right. So there's F. How big is F? Do you remember the equation called Coulomb's law?
Well, that's K times Q1 times Q2 over R squared.
Okay, so there we have all the information, including applying the force equation. Now the question says, what's the magnitude and direction of the Coulomb force that the negative charge exerts on the positive charge? Can you answer that now? I know I said some people can answer instantly when it was posed, but I wanted to make sure we thought it through. Can you answer that now? What direction is the force on the black charge? To the left, because as Claudia said, they're opposite signs, so they're attractive. And how is that force going to compare to the force on the first charge? Okay, negative because the opposite direction, right? So I'm just going to put F here because my arrows are already opposite direction. So the answer is indeed negative F. We could have answered this by saying, okay, the forces are attractive, so if one's to the right, the other one's got to be to the left, so they're attracted toward each other. And we could have said, since the force equation is just magnitude of one charge times the magnitude of the other, it's just the product of the two that matters, not which one's which. Or we could have gone back to like the second week of the first semester and gone to Newton's third law. What does Newton's third law say? For every action, there's an equal and opposite reaction. That is, for every force that object 1 applies on object 2, there is an equal and opposite force of object 2 on object 1. They have to be paired. They have to be through the same force. You can't be comparing gravity to electrostatics, for instance. But the electrostatic force between the two is going to make a Newton's third law pair that have to add up to 0. And so it had to be minus F, so F plus minus F equals 0. So even with no knowledge about static electricity, you could have answered this correctly. So you have two different ways of looking at it. As long as you understand and can do it, I'm happy. Now to electric field. Okay, so I only had one slide before we got to electric fields. Electric fields. You are intimately familiar with force fields. I mentioned this the first day of school, right? What force field are you familiar with?
Gravity.
Gravity. Now let's focus on gravity. What direction is the gravitational field? Okay, it's toward the center of the Earth. Well, I'm talking about on the surface of the Earth. We're being more general. On the surface of the Earth, the gravitational field is pointing toward the center of the Earth. That's how we define down, after all. Because gravitational force is always attractive. And we found the magnitude of the force of gravity by taking the gravitational field, G, and multiplying it by a gravitational charge. What's the gravitational charge? The mass. We do exactly the same thing with electric force. So we had before that the gravitational force was equal to the gravitational charge times the gravitational field. Or the gravitational field is equal to the gravitational force divided by gravitational charge. That's what we had before. We didn't use terms field and charge. We just said acceleration of gravity and mass. But that's what it was. So we're going to do the same thing now and define the electric field is the electric force vector divided by Q, and the electric force is equal to Q times the electric field. Notice those equations are exactly analogous except for I wrote them in reverse order. I put force as the leftmost and the rightmost, and fields are the middle ones. So everything we learned about how gravitational force works just the same with electric field and electric force, except for one peculiarity. Gravitational force is always attractive. Electric force could be attractive or repulsive. Now, for calculational purposes, we choose to use a positive Q in our equations. So the electric field, looking at this equation right here, the electric field is going to point the direction that the electric force will be if Q is positive. If Q is negative, it's going to reverse things. So the electric field is going to point the direction that the force will be if Q is positive. So what is Q? Notice here we have a capital Q and a lowercase q. The lowercase q is what we call a test charge. And you're like, test charge? I don't like tests. The test charge is, in most cases, well, we use the word test charge in all cases, it's a theoretical charge. You're saying, what if? If I put a positive charge at point P, what direction will the force be? In this picture, capital Q, as indicated with the minus sign, is a negative charge. So if I have a negative charge and I put some random positive test charge outside of it, what direction will the force be? Okay, attractive. All I cared about was attractive because that's always going to be clear. Toward each other is absolutely correct. So it's an attractive force. So on my test charge, it's going toward my negative charge. That's then the direction the electric field is going to be. So electric field should always point into a negative charge. Now, if my capital Q had been a positive charge, then instead of being attractive, the force would have been repulsive. And so what direction would the electric field be? Out. So here's our first rule of electric fields. The direction of the electric field is always going to be going into a negative charge and out of a positive charge. It doesn't matter what else is around. That's going to be a fact. So electric field points into negative, out of positive. Now, a second question is, what's the point of electric fields? I've introduced this field thing, and I didn't introduce why you would ever want to use it. What was the point of the acceleration of gravity? And think about just forces. When we talked about kinematics, we sometimes didn't talk about the dynamics, that's the force of gravity that made things. We just said G. But what was the point of G?
Ask the question in different words. I don't understand what that's.
It's like a spelling bee. Can you use it in a sentence, please? Use it in a different sentence. And now I have to remember what the question was.
What's G in that
Yeah. What was the point of using the gravitational field G instead of every time using force of gravity is equal to capital G times M1 times M2 over R squared?
Makes it like simpler.
It makes it a lot simpler. That's the same reason we use electric fields. It makes it a lot simpler to find the force. So electric fields aren't some magical thing. They are a calculation to tell us how strong the force would be if I put a charge here. And it makes it a lot easier to find the forces. So here I just have the two equations I had in the previous slide. I was like, I'm not sure which my next slide has. I want to actually apply this, but after this, I didn't do a woo clap thing here. You just have to answer. A point charge has a net charge of minus 10 nanocoulombs. What direction do the electric field lines point? Into the charge, right? The whole north, south, east, west. It depends on where you are, which one of those might be correct. But the one that's always correct is into the charge. Yes?
How did the point charge is always positive?
The test charge. Point charge means, hey, here's an actual, okay, I say actual. Points don't exist in reality, but here's an actual charge of very tiny size. Whereas test charge is what we use to describe the other one, which is what the test charge idea is. If I were to put a charge here, what would happen? And that's what's always positive, is when you're asking the question, if I were to put it here. That's a good thing to point out, though. We do not want misconceptions. This problem here was actually going to be the next step in our class on Wednesday. So here I have an electric field problem, and I will work through this. I think I can do it on this page. I didn't check how much space this can take. A small sphere with a mass of 5.10 grams is hanging vertically from an insulating thread. Important that it's insulated so you don't have charge leaving the sphere. That is 12 centimeters long. By charging some nearby flat metal, you don't have the basis to understand this aspect yet, but basically there's something here that's making a uniform electric field. When I say uniform, what that means is the electric field has a constant strength regardless of where I am and a constant direction. The strength of the electric field is 7.20 times 10 to the fifth N divided by C. What does N stand for? Newtons. What does C stand for? Coulombs. Where does that come from? Whoops. That wasn't what's supposed to happen. That comes from, that was genius. I have to do 2 clicks to get past this. Okay, maybe more than 2. If you look at this equation for electric field, the unit of force is a Newton. The unit for charge is a Coulomb. So electric field is in units of newtons per coulomb. We will learn later that that is equivalent to a volt per meter. So we will have two different alternate units we'll use for electric fields. Right now, we haven't defined the volt. So the second one here doesn't make sense at this point. Just pointing out to you now, so when later on we have an electric field that has units of volts per meter, you're not like, Okay, so that's why we have the units of newtons per coulomb there. As a result, the sphere is displaced 6 centimeters horizontally. So the first question, what is the angle that the thread makes with the vertical? What methods do you think I should use to find the angle?
Trigonometry.
Trigonometry based on?
The distances and lack of an angle.
Okay. Based on the distances and the angle. So we have everything we need. What side is 6 centimeters? Opposite. What side is 12? Hypotenuse. What trig function relates opposite and hypotenuse? So I have sine of theta is equal to 6.00 centimeters over 12.0 centimeters. Or as David astutely pointed out, 1/2, which means that theta is equal to
45 degrees.
30 degrees. Those are ones that we memorize. Well, in high school, we were forced to memorize what the values for 0, 30, 45, 60, 90 were for sine, cosine, tangent. Maybe you weren't forced to, but it served me well as a physicist, trust me. Okay, so we have the angle. Great, it's just trigonometry. What's the tension in the thread? I will use Newton's second law. If I'm going to use Newton's second law, what do I need to do? Draw a free body diagram. So my forces, I have a downward force. Force of gravity equals mg. I have a horizontal force, which is, what is that horizontal force? It's Q times the electric field. And then I have my final force, the force of tension. Which I don't know, right? But Newton's second law says sum of the force vectors is equal to ma. And in this case, it's not accelerating, so that's 0. And once again, I have the easy case of only 3 forces. So that means I can make a triangle, and my triangle is going to look just like the triangle that already exists. I'm going to have mg, qe, and ft. And we already know the angle there, 30 degrees. So given that triangle, I can now find what the force of tension is. How would you like to do this? There's only one way. We know the mass, we know g, so that gives us the adjacent side. And we're looking for the hypotenuse. So what trig function relates adjacent and hypotenuse? Cosine. And so I'm going to have cosine of 30 degrees is equal to mg over the force of tension. Therefore, force of tension equals mg cosine of 30 degrees. We have m right there, 0.00510 kilograms, g 9.8. Multiply that by 0.866, because that's cosine of 30 degrees, because we had to memorize that. And you have a number. I'm not doing the number because it's just math. It's going to be in newtons. Then we go stay. Believe me, nothing mortifies me more than leaving class with a mistake.
Did you really?
Nope. That's why I asked if I had a mistake. Thank you. Appreciate it. Like I said, nothing mortifies me more than leaving the classroom with a mistake. We all make mistakes. You guys have all taken a test. You probably figured that one out. Doesn't mean you don't know it. Right, folks? Just because you missed one or two on a test doesn't mean you don't know your physics. Okay, so if I put in my m, my g, and my square root 3 over 2, that's what 0.866 is, I will get my answer. What is the charge on the sphere? How would I find that?
Shouldn't the charge of the sphere or the force exerted by the electric field?
I will find it from that.
Okay.
It's not equal because force and charge aren't equal. But I will take this and I'm saying, well, if I can find what this force is, if I can find force E, that's QE. So Q is just the force there divided by the electric field. So once again, using trigonometry, at this point, we know what this force and this force is. I could use the Pythagorean theorem to find what this force is. I could use tangent to find what it is, or I could use sine to find what it is. Any one of those would work. My preference is to use tangent because if I use tangent, then I don't have a calculated force tension, so any round off there doesn't propagate. That's my preference, just to make sure I have as clean an answer as possible. So I would take this and I would say tangent of 30 degrees is equal to opposite QE over adjacent MG. I'm trying to solve for Q, and I'm going to do my math right this time. Q is equal to MG tangent of 30 degrees over E. There you have it. Now, as you look at this, there was only one thing that you haven't done in the past in this problem, and that was force is equal to QE. But that doesn't mean the problem is trivial, right? It's a lot of stuff that's kind of buried in your memory. You have to pull it back. We did it before. Got to be able to do it again. Any questions?
Why not use it?
The only reason not to is because any round off that I made in calculating FT would then be a larger effect on my answer here. So it minimizes the round off there. That's the only reason. So it would still be right. I'm like, if you're doing it for homework, and if you're keeping 6 digits in your number, it's not going to make a difference. So it's more personal preference, just so I don't have to worry about propagation of error. Do you have a question?
Yeah, just to confirm that Q is the point charge
Yes.
and E is the electrical field.
Yes. Good questions. Those are the new things after all. Okay, now, the electric field for a point charge. We learned Coulomb's law to relate to point charges. So if I go back a whole bunch of slides to this one here, if I'd used Coulomb's law to find the force, I would have had the force between the two was equal to K capital Q. Capital Q is the actual charge that's causing the electric field. That's our sign convention. Times lowercase q, our test charge, divided by the separation between the centers squared. That would be the force, just as we learned to calculate last class period. And now with the idea of the electric field, my electric field is defined as force E over lowercase q over that test charge I have a q over a q now, so those q's cancel. And it's k times the physical charge present divided by the distance from that charge squared. Now, I didn't make this a vector equation. I just found the magnitude. What's the direction? And it depends on the sign of q. What is the direction going to be? Yes. I just found the equation, the electric field magnitude is k capital Q over r squared. What direction will the electric field vector have?
Isn't Q like in this problem, like what it's showing to be negative, so therefore it's going to be.
Right. If Q is negative, it's going in. Same equation, if Q is positive, it would be going out.
But what I'm confused about is like, wouldn't we see the negative in that like equation?
Right. So traditionally, what we would write for this, taking into account exactly what you said, is we would write the electric field vector is equal to k capital Q over r squared times r hat, where r hat is the vector that points from the center of the sphere. Well, it's a unit vector, so it has a magnitude of 1, but it points from the center of the sphere out to where the point is.
What does that have to do with the negative?
If capital Q is negative, it's going to reverse the direction. Right? With that equation, if capital Q is a negative number, that's going to be in the minus r hat direction. If capital Q is a positive number, it's in the positive r hat direction. Right? That was what you said. If Q changes sign.
Okay.
Sure.
How did you get it, the second part of the green thing, FE over Q negative, that comes from the formula?
This here?
Yeah, how'd you get that?
Okay. I substituted this here for this here to give me that. And then I had to divide by Q. That was that. I separated them out so I could cancel them and still have what I wanted. I'm going to erase all of the stuff I just wrote because it will muddy things up when you look at the slide later if you do.
So if the charge was opposite, if it was positive, like that's what the thing, then the arrow would be going in the opposite direction, and what would the R look like then?
Well, the R hat is still R hat. Remember, the hat means it's the magnitude of 1.
Right.
It's important that we don't get that confused. And so it's still pointing from the center of capital Q to where lowercase q is.
Okay.
And so if capital Q is positive, then the direction is that direction. If capital Q is negative, then it's negative in the outward direction, which means it's in the inward direction.
Oh, okay. Okay.
Okay, go forward to where we were, maybe. All right, I believe this is where we left off. And so you can see the electric field magnitude there. Because I did just magnitude, I put absolute value on the Q. But as we saw, if I put the vector, you put the R hat, and you take away the absolute value. So electric field due to a point charge. The electric field due to a point charge is often not very exciting or easier than if you just use Coulomb's law. But if you have a whole bunch of charges, it gets more interesting. Because if you have a whole bunch of charges, you can all look at David right now. He has a homework problem where he has a whole bunch of charge spread out over 2 pieces of wire. And what do you have to do, David?
Apparently you have to integrate.
Apparently, guess what I'm doing after class with David?
Yes.
You have to integrate. It's not so easy when you have a whole bunch of charge. So what do we do for the rest of us who don't do calculus? Well, I'm sure that was a constructive comment. I'm just going to move on. We calculate the electric field due to the complex geometry, and then we just work with that electric field. And we will learn a little bit about Gauss's law that allows us to fairly easily find the electric field for some complex geometries, only a very limited number. And then we use that, and how that's done is by adding up all of the vector fields. Now, in David's problem, fortunately for him, the direction is all in one direction. He doesn't have to break it into components. If he did, I probably wouldn't give him a problem. So how does that work? Well, let's start by looking at a simple problem with 2-point charges, right? We're not going to do a problem with 20-point charges. If you can do it with 2, 3, maybe 4, you could do it with 20. It would just be an incredible amount of work. So here I have 2-point charges plus, well, Q1 and Q2. Q1 is positive, Q2 is negative. We have the geometry and the picture already made for us. Charge of 0.60. Okay, this is the dumbest question I asked, but I ask it just to make sure we're all still remembering from first semester. What do I even call that symbol in front of the C? 0.60. Okay? It's the Greek letter mu, and it stands for micro, and micro means 10 to the minus 6. Just have to make sure we stay comfortable with that and we don't I don't know what to do with this value. So that's 0.60 times 10 to the minus 6 coulombs. It's located x equals 0. Charge of 0.50, negative 0.50 times 10 to the minus 6 coulombs is located 0.40 meters away. And point P is where I'm going to find my electric field. It says, what's the magnitude and direction of the electric field at this point? Now, the last slide said we're going to calculate the electric field from each of the individual point charges and add them together as vectors. What we learned in class on Wednesday was when we're doing something like this, we don't worry about one charge interfering with another. Remember when we were talking about how to add the forces with multiple charges? But don't worry if there's one in between. You just calculate each pair and go from there. So that's what we're going to do here. So my equation is the electric field magnitude is KQ over R squared. It's going to have direction, and I'm going to indicate direction by plus sign or minus sign. Notice plus will be to the right, minus will be to the left. So E1, technically it's a vector, but I'm not writing it the vector sign because we're one-dimensional. E1, the electric field due to charge 1. Is that going to be pointing out at point P to the right or to the left? Charge 1 being a positive charge. Electric fields point which way from positive charges? Outward. And so going away from Q1 over here at point P, missed, is going to the right, which we're calling positive. So E1 is going to be a positive value. K, now the capital Q becomes lowercase q1 for that charge. And what is, go ahead.
How is it going to the right and pointing out?
That's pointing away from Q1.
I thought that Q1 and P repelled each other.
They're what?
That Q1 and P repelled each other if they both are positive.
Right, if that's right. If I had a positive charge here, its force would be that way. It'd be repelling.
Wait, is P not a point charge?
P is a point where I'm putting a test charge. A test charge by definition is if I were to put a positive charge here, what would happen to it? Right, that's why we go through these samples so you can take those ideas and put something solid to it. So if I had a positive point charge here, I'll put plus Q. That's my test charge. I'll put in parentheses so it's clear that it's not really there. I'll even put test charge. Then the force due to charge 1 is going to be repulsive. It would be to the right, which because of this arrow is positive.
What is your letter at the top? You have E1 equals
That's a Q1. And then we have to divide it by R squared. R is the distance between, since I'm looking at Q1 in my test charge, which is 1.20 meters. Whoops. Okay, somebody want to give me an actual number for that? I know you said a number. Okay, can you say it again? 0.8? And what are units? Newtons per coulomb. Because I use SI, I can go through here. My meter squared on top cancels with my meter squared on bottom. My coulomb on top cancels with one of the coulomb squared on bottom and left per coulomb. Okay, so that's electric field due to the positive one. What about for the negative one? Notice I put absolute value around this one. I should have put absolute value around this one, but it was positive and I didn't remember to. Because I'm finding the magnitude and then I put the minus out front because I've already determined the direction based on the sign. You notice that Aaliyah recognized because Q2 is negative, that would be attracting a positive test charge, so it's going to be going to the left. And since right was positive, it's a negative. And the separation between these is 0.80 meters. And so what do we get from that calculation?
Negative 7,021.56.
Okay, so what is the total electric? Well, absolute value. It is important to pay attention to signs, right? You could easily make a mistake here. So if I add these two together, I'm going to have, what do we have? Somebody just do it for me. 3, 2, 6, no, 3, 2, 5, I don't know. What is it? 3, 2, 7. Okay, I'm going to stop there because how many sig figs do I really have? Yeah, it was 2 in the first calculation, so that was good to 3,700. It was 2 in the second one, that was good to 7,000. And so I kept more digits so I wouldn't lose something in rounding off. So there's the correct answer. Minus because it's going to the left. I don't know, it feels kind of funny to be doing these. I don't know what. We know it's going to the left because it's a negative sign and we hit define plus x is to the right. It was a different question.
How do we know that the going outward?
Okay, how do we know that going outward from positive charge is this way? It starts with where is our test point. So outward from here to that test point is going to the right. Right, if the test point had been here, outward would have been up. If it had been here, outward would have been to the left. So it's based on the geometry of where they are. Okay, now one for you. And this will take the rest of the class period. Just get started with it. You won't have time to finish it. 3-point charges are placed at the corners of a rectangle. What's the electric field due to these charges at the fourth corner? So you're trying to find the electric field at this point due to those charges. And of course, what's the acceleration of an electron? We're not going to have time to answer that in class. As with yesterday, you have to do the one where you add components. You're not going to have time to just set it up. By the way, I'll point out one more thing. Notice the last sentence. Assume that no forces other than that due to the electric field act on it. At this point, unless you have something that specifically invokes gravity, we're going to ignore it. The reason, if you have charged particles in close proximity, the electric force is usually orders of magnitude larger than the gravitational force, thus you can ignore it. There are some cases, like the problems we did previously, where we couldn't ignore it, but those were kind of unusual. Okay, now I know I told you don't have enough time. I want to cut in now because you're not going to have enough time to finish, but you have enough time to thought your way how you're going to do it. I heard people say, "Are we going to have to do that?" What do we have to do? What? Obviously, I saw everybody drawing pictures. That's the first step. Then what do we do?
Calculate the charge for each point.
Well,
Oh, figure out the direction of the charge.
okay. I put that as a second thing, but you can do it first. My first thing is calculate the magnitude of each field.
Oh, that's what I meant. I said charge.
And so I'm going to label things A, B, just so I can write things quicker. And so I'm going to have E1 has the magnitude of K absolute value Q1 over A squared. E2 is K magnitude of Q2. Pythagorean theorem says that the distance from Q2 to P is A squared plus B squared. E3 is equal to K absolute value of Q3 over B squared. And then I have to go with what Andy actually said. I have to break these into the components. Question?
Wouldn't all the K's be negative in this case?
Well, I don't really count two, so I wasn't taking into account any signs. K itself is positive, but you were saying the E's be negative.
Right.
And-
K's
and-
would be negative.
That's going to come into the next step of determining direction. Go ahead.
I didn't think they were all negative or positive. I thought Q3 was going to be.
I haven't gotten that far yet. So let's look at that. Starting with Q1. Is that attractive or repulsive? Repulsive.
Oh, oh.
Because we're putting a positive test charge at P.
Which one's E1 again?
Q1 is this one here. So E1 is the one going with that. So if I define my positives in the standard, actually it's shown down there, then that means I'm going to have E1 is equal to minus K Q1, I'll still put absolute value there, over A squared in the X direction. So now I've put it into a vector in components.
Wait, what? Why is it attractive?
It's repulsive because that's a positive charge. And so going away from Q1 is going to the left.
But if you did the other way, if you just like if your direction were the other way,
If I had my directions defined like this, yeah, it depends on how you have them. And that's why you have to define it. If you don't define it, you really don't have what you need. Maxwell. Well, the electric field itself is always going to be pointing to the left here because this is a positive, so it's pointing away.
Question is if it's negative or positive.
Yeah, and so if X is defined as positive to the right, then that's negative X. Okay, so there's our E1. Let's do E3 next because it's also easy. E3, that's a negative charge, so does the electric field go into or out of a negative? Into, so that means it's got to point down, which is negative Y. And change color just so it stands out. So minus for down. Oh, come on. And then the final one, we have, oops, that was not the right button. That's the right button. We have to actually be most careful. 2, it's positive, so it's going out. So E2 is going like this. And so that's going to be left and up. So the Y component is positive. The X component is negative. And so for the X component, I'm going to take this triangle here, and I need to calculate this side here based on that one. So if I use this, that would be cosine, but all I really need to do is, this is A over square root A squared plus B squared. That's what cosine is. And we said that's negative, so don't forget the negative sign. Plus, and then for sine B, I didn't put any numbers because we're already over time. I used A and B to make it shorter to write, but there I would have the components. The last step would be add the x's together, so this and this to get my total x component. Add the y's, so this and this to get the total y's. You can see it does build up, and that's why we don't do like 7 or 8 charges, because it's going to be a nuisance to do that. Have a great weekend. Remember, no school on Monday. It's a long weekend, Martin Luther King holiday. If you haven't been to Martin Luther King Memorial there in Washington, D.C., it actually is really powerful. And we'll see you in lab on Tuesday.